Welcome back to another video with us here at LMD and STEM Academy. In this video, we will be working through the June 2023 Physics Unit 2 Paper 2, and we're working on the Module 3 question, which was the question 3. So in part A, it says define each of the following terms. And so we're given these terms, the work function, the threshold frequency, and the cutoff wavelength, okay? So here are the definitions for these terms. So the work function refers to the minimum energy that's needed to free the electron from the surface of the metal, and it has units of joules. So generally, this is how we would denote work function. We would denote it as phi, so it's a open circle with a line through it. So that's your work function. Okay? Threshold frequency now, we generally denote it as F naught. Okay, so that's how we denote threshold frequency. And the definition of it is that it refers to the minimum frequency required in order for the electrons to be emitted from the metal surface. So that's a minimum frequency, okay? And of course, it's a frequency, it's going to have units of hertz. All right. The final one that we have to define is the cutoff wavelength, and that's generally denoted as lambda naught. Okay. And the cutoff wavelength now, this is a maximum wavelength of the incident electromagnetic radiation that's required for electrons to be emitted from a metal surface. So if we think about this one, why is the maximum wavelength? You know that the longer wavelength you go, what does that mean? You're getting lower and lower in energy, right? So there's a max wavelength, right? That if you go beyond that, you're not going to be able to get the electrons to come off, right? So there's a maximum wavelength there known as the cutoff wavelength. Okay? All right. And so let's go ahead here and see what part B says. So part B says the figure below shows the apparatus used in a photoelectricity experiment. S is a source of variable frequency UV light. So that's S here. That's coming through this quartz window here. And the cathode is polished. It's a polished metal surface, right? So out here is a polished metal surface. The cathode here specifically, right? And so the difference, potential difference between the anode, which is here, right here, and the cathode can be measured by the voltmeter, right? We'll see that reading down here, and that can be varied in both directions, right? The photoelectric current flowing between them is measured by the microammeter. So here's a microammeter, right? So that's what we're working with. This is a photoelectric experimental setup where we have our cathode, which forms a metal surface, and we have our anode, which is going to be what? Positively charged, attached to the positive terminal, right? And so that's what we're working with. Okay, so let's go ahead now. All right, so with reference to the apparatus in the figure, explain the term stopping potential, right? So again, remember, this is our metal surface here. This is our cathode. And generally, that's what? Negatively charged. And then we have our anode here, which is positively charged, and that's where the electrons are running there. The electrons themselves that leave the metal surface, they are negatively charged. They're going to be repelled away from the cathode, and they're going to run towards the anode, which is positively charged. The anode is attached to the positive terminal of the battery, so you can imagine that when the circuit is closed, you have the anode being attached here. So that's a positive terminal. That's why it's positively charged, right? Just a positive potential. And then the cathode would be attached to the negative terminal of the battery. And so it is at a negative potential, okay? So then a potential difference is established between the two, right? So there's a potential difference in this region here. And it's that potential difference that allows the electrons to run along in that direction towards the anode. Okay, so if we're supposed to explain this term now called stopping potential, let's think about what's going on in a photoelectric experiment, right? Generally, this is the general setup, right? where you have the anode being attached to the positive terminal, the cathode attached to the negative terminal. So as we said, you're gonna have flow of electrons in this direction. And do you know what a flow of electron means? A flow of electrons means that you're gonna have a current, right? And so we can measure a current whenever we have this PD here in this direction and the electrons are flowing from one end to the other. Now, what happens if we reverse the polarity, right? If we reverse the polarity and we make this now, I'm going to use different colors, right? If we reverse the polarity and we make this one now negative and that one is positive, what does that mean for our electrons, right? The electrons are going to be repelled from the anode. They're not going to want to go where it's negative anymore. And so we're not going to have that nice flow. They're going to want to stay in this cathode region here. Okay, the electrons are going to want to stay there. Once they escape the metal surface, they're going to want to stay there. So we're not going to have that nice potential difference anymore. And we're not going to have that flow of electrons, right? And so let's talk about that now. Let's bring up what we have here. So if the polarity of the DC power supply at the anode is reversed, as I'm showing in my green, if I reverse and now I have those colors there, what's happening? The anode is going to become more negative and the electrons are going to be repelled from the anode. Okay, the electrons are going to be repelled, so no current is going to flow. And this happens at what we call a negative potential difference called a stopping potential, or that VS there. Okay, so remember, the potential difference at which you're not going to have the flow of electrons, so you're not going to have any current, is what we call our stopping potential. And that's arrived at when we reverse the polarity of the anode and the cathode respectively. Okay, so let's just wrap this up with a nice definition of what the stopping potential is. So the stopping potential then is the potential difference that causes the photoelectric current to reduce to zero. So the microammeter is going to read 0. When the microammeter reads 0, right, your current, your photoelectric current is going to be 0. And that corresponds to your stopping potential. And that means that none of the electrons are reaching the anode, okay? None of them are really reaching the anode, so we're not going to be able to measure any current, and that's VS, right? That's what the voltmeter would read. That's whatever that reads is our stopping potential when the current is 0. All right? Okay. So let's go ahead now. So part C says the graph below was obtained in one such photoelectric experiment in which the frequency of the light source F was varied and the corresponding stopping potential was recorded. Okay, so if we go back to our little drawing here, what they're saying is that, you know, this light source here, they're varying the frequency that comes in and then they're measuring stopping potential. Okay, in response to that. So see, you're varying your frequency, and your stopping potential is responding in corresponding to that. Okay, so that's what we have here. We have this graph here where we're flat up to this frequency here. And then we see that the stopping potential gradually goes up there, okay? All right. So remember, we always like to just take into account what our units are, just so we don't get tripped up. So that's in volts, that's stopping potential, and the frequency is in times 10 to the 14 hertz, okay? So those are good things to get our bearings on. So let's go ahead now. So it says write the general form of the photoelectric equation and rearrange it to show the relationship between the stopping potential and the frequency as it's shown in the graph. So this is a graph, right, as you can see, and there's like a line here. So it's like a linear relationship that's established here that we can see. Okay, so let's start by writing the general form of the photoelectric equation. So the general form of that would be that HF is equal to phi, which is your work function, plus your EK max. Okay, that's your maximum kinetic energy. The work function can also be written as H F naught. So your H times your threshold frequency. So we're just going to substitute in that for work function. And your EK max can also be written as EVS. So that's the charge on an electron times the stopping voltage, okay, or the stopping potential. So what do they want us to find? A relationship between Vs and the frequency as shown in the graph. So we're gonna make Vs our subject then, okay? So to make Vs a subject, I'm gonna bring over the HF naught to the left-hand side. So I'm gonna have HF minus HF naught being equal to EVS, right? And then I only want Vs, I'm gonna divide both sides by E now. Divide both sides by E. So now I'm left with HF over E minus HF naught over E being equal to Vs. Okay, so what was Vs? Vs was on our Y, right? So we can say that this is my Y variable, right? F naught, all right, let's do this one. F is on my X. So the F itself is my X, right? And you know, when we're linearizing these equations, you know that the thing that's beside the X is generally your M, right? So that's your M, which is your gradient. So that's my M, which is my gradient. That's the gradient of that graph. And so the gradient is equal to H over E. That's what that equation tells us there. And then this part now is going to be your C. So let me just put that in a color here. This whole part is going to be our C, or our intercept, our Y-intercept, okay? So that's how all of this is related to the graph. So that's your C, and it is your Y-intercept. It's where that line cuts the Y-axis. So it's your Y-intercept, and that will be equal to HF naught minus HF naught over E, or we could say that that is equal to minus the work function, because work function is HF naught over E. So that's what your Y is, or your C. Your Y-intercept or C is that. Okay, your work minus your work function over E, which is the charge of that electron there. All right. So now we have everything, but for intents and purposes of the general form that they wanted us to show, it's just this one here. So let me just box that, right? I went ahead to show you how everything is correlated to what's on the graph, but for submitting an answer, this is all that would have been needed, okay? So that's our answer, is that HF over E minus HF naught over E is equal to Vs, or your stopping potential. All right, so let's just keep this equation here handy and in mind, because we're going to need it going forward. All right, so let's clear this and go ahead. So now we're being asked to determine the gradient of the line on the graph, right? So the gradient, you know, the generic equation for gradient is going to be rise over run, right? So it's going to be y2 minus y1 over x2 minus x1. So that's going to be your gradient. And we knew from earlier that this gradient here is also equal to what? We said that this gradient was also, we know, is equal to H over E. So let's just keep that in mind, that that's what it would be equivalent to. But let's calculate it now from the graph, right? So I'm going to take this as my y2, that point right there. And I'm going to just use 0 as my y1, right? The x that corresponds to my y2 would be 8. So this guy is this right here that corresponds to my y2 is my x2, and that is 8, right? And then this guy right here that corresponds to my x, that's x1, it corresponds to my y1, which is 0, right? So my y1 is there. And so that's my x1, and that is 4. So my x1 is 4, my x2 is 8, my y1 is 0, right? That's 0. Okay. So this is my rise over run. And so when I plug in the values now, I'm going to plug in my y2. So each of these little tiny squares is 0.04 because 10 is 0.4. So one of them would be 0.04. So if I'm right here, I'm at like one square above, one tiny square above 1.6, that's 1.64. So that's 1.64 minus y1, which we said we're taking 0. We're taking that one. So 0 divided by my x2. So the x value corresponding to my y2, which is 8, minus my x1, which is the value corresponding to my y1, which is 4. And remember now, you know, that this is all times 10 to the 14. That's what the label on the graph told us. So when I do that and I work that through, I'm going to come up with a value of 4.1 times 10 to the minus 15, and that's going to be in hertz to the minus 1. Right? The top would have been volts and the bottom is hertz to the minus 1. So what would that be? That would be volts, hertz to the minus 1. All right? So that's V, hertz to the minus 1. So that's my slope. That's my M. So that's what we would box. That is my M, which is also my H over E. Right? And so that is our answer here. So let's just box this one. So that's my slope there, my gradient of that line. Okay. All right. So let's go ahead now. All right. So let's go ahead. We've just found our slope. So we have that H over E. So now we're being asked to determine the value of the percentage difference between the experimental value of H over E that we just obtained in C part 2 and the calculated theoretical value of HE. So we're going to calculate the theoretical value of H over E using the standard values of H and E given in the answer booklets. So at this point, we know our experimental HE. So we're just going to write that down. We're going to write that back and then we're going to find the theoretical one by consulting the table. Okay? So here's what we're gonna say here. We can say that from C part 2, right? We know that the H over E, right, which is your experimental one, right? That's your experimental value. So I'm gonna write H over E, EX experiment. So you know that that's the experimental value is equal to, what did we just get? 4.1 times 10 to the negative 15 volts per hertz, right? That's what we got. So we know that that's from C part 2. So now we're gonna have to find HE theoretical. And we're gonna have to consult our data booklet. So we're gonna look at the very first page in this whole thing, right? That we're provided within the exam to get the theoretical one. And so we know that H, right, theoretically, that's Planck's constant. So that's 6.64 times 10 to the minus 34 joules second. And then the E, again, is just a charge on an electron there. So we'll put that as minus 19 coulombs. And so when we work that through, we're going to come out with a value of 4.14 times 10 to the minus 15, 4.14 times 10 to the minus 15, again, it's gonna be the same unit as that one. So we can just write that there for now, that it's the same unit, right? Because it's H over E, so they're gonna have the same unit. So we're comparing these two things. They want us to find the percentage difference, right? So when you're finding the percentage difference between the two, what you're gonna do is literally subtract subtract the smaller from the larger. So we see that there's a difference. We see that the theoretical value is larger than our experimental value, right? We see that here. So the percentage difference will be my larger value, which is the theoretical value, minus my experimental value that I got 4.1 from my gradient, from my slope there. Then we're gonna divide that by the smaller of the two, which is the 4.1, the experimental value. And then once we do that, we're gonna multiply it by 100. Okay? So when I do the difference between the top, I come up with a value of 0.04. So I'm pretty much dividing 0.04 times 10 to the minus 15. I'm dividing that by 4.1 times 10 to the minus 15. And then multiplying that by 100. Right? Of course, you know, that would go. And so in the end, I'm going to end up with a value here of 0.97%. Okay, so that's our answer here for the percentage difference. So let's just write that percentage difference. And then we're just gonna box that in, lock that in. That is our final answer here for the percentage difference. Okay, let me just make that box a little bit smaller. So that's our thing. 0.97%. That's the percentage difference between the experimental H over E and the theoretical H over E. Okay, so now we have to comment on the result obtained in C part 3. Essentially, they're saying like, why do we have this almost 1% difference, right? So that's due to experimental errors. Like really, a lot of these things can come back to just experimental errors and how the experiment was executed, right? So experimental errors in measuring the stopping potential in response to the change in frequency, right? So there are errors there. You can imagine that there are a variety of sources of errors there that we could get. So maybe voltmeter not as accurate, right? Voltmeter not properly calibrated, stuff like that, right? What else could have been? So we have the voltmeter not properly calibrated. That's a potential experimental error. Bam, bam, bam. What else? Yeah, I think we can just stop there for now. I mean, the thing is just that we capture that there's experimental errors that would make our experimental value different from the theoretical. Always, that's what you go to. And then we can start to think about why. So the voltmeter is not properly calibrated. Recorded, readings not recorded as accurately as they should be, right? And so those will lead to those minor differences that we see here, okay? And so that's why I would say that a roughly 1% difference in what we see experimentally versus what was the theoretical, okay? And so with that, we're done with this, this part 5 here. All right, so let's clear and go ahead. All right, so what are we doing now? So we're at part 5. Okay, so that was part 4 that we just did. So we're at part 5 now, and we're extrapolating the line on the graph in the figure below to find the intercepts or y-intercept on the VS axis. And then we're going to use that value, that intercept value, to find the work function of the cathode material in joules. So they're telling us which unit they want it in and everything. All right, so let's go ahead now. So we're literally, for the extrapolation, all we're doing is we're taking this line and we're extending it all the way down until we cut our y-axis. That's what we call our y-intercept. So let's go ahead and see what I have here when I did that. So here's what happened when I did that. I extended my line down, down, down. And when it cut the y-intercept, it cut at a value of what? What is that? I remember I said each tiny square is worth 0.04. So I ended up at 1.6 plus 2 tiny squares. So that's 1.68. That's what I got for my y-intercept. So that's minus 1.68 volts. So let's just jot that down, right? My y-intercept, the value I got was negative 1.68 volts. Remember now, what did we say our y-intercept was? We said our y-intercept from our derivation earlier, we knew that that y-intercept was HF naught over E. Okay, so that's what's gonna then be equivalent to this value that I got, right? So now that I got this value, look at this nice thing here at the top, nice shiny thing in the top, right? What is that? That is our work function, right? That's our work function. And so all that we have to do then if we have to find the work function is that we have to just make this a subject and then bring over the E. That's all we have to do. And in bringing over the E, guys, we're going to end up with our stuff being in joules. So that's nice. So let's write this down here now. That's our work function. That's what we're trying to find. So I'm going to put that phi, right? So that's my phi, that's my work function, over E is equal to minus 1.68 volt. And remember, this was minus, right? There's a minus before that from our earlier derivation. So we just drop the minus there too. And what that means is that this negative sign is going to go away, right? The negatives are going to cancel out each other. So in the end, what do we have? We have that our work function is going to be equal to the 1.68 times the E, which is 1.6 times 10 to the minus 19. And so when all is said and done, our work function in joule is gonna come out to be 2.69 times 10 to the minus 19 joule. So that's our work function for that cathode material, okay? So I'm just gonna box that. Locking in this for our work function. Okay, so remember now the key thing is to know that, okay, I got my y-intercept by extending this line. When I got my y-intercept, what does that literally mean? That means that I found my minus HF naught over E. HF naught is your work function. We know that from before, so we can just sub that in here. And then all we have to do is transpose. So bring over the E, and then we find our work function, and that's what it turns out to be. All right, and so with that, we're gonna move ahead now. So let's clear this and move ahead to part D. So part D says that the figure below is a sketch of a graph showing the variation of electron photocurrent, IP, with an anode cathode voltage for a specific level of UV illumination of the cathode. So you have a specific UV light, specific frequency that you've chosen, right? And you have a current that flows, and then you have the potential difference here. So it's a photocurrent versus potential difference plot that we're looking at here. All right, for a specific frequency. So this is just one frequency that we use to generate this curve. All right, so let's go ahead now here. It says for each of the labeled regions on the graph in the figure below, state what happens to the flow of the photocurrent and explain why this happens in each case, right? And so in order to do this explanation, we can go back to our earlier work. Earlier, we were talking about, how we would measure a stopping potential and just how the whole photoelectric experiment apparatus works, right? And so that's what we need to use to explain what we're seeing here from a photocurrent standpoint, right? What we're explaining here, really fundamentally, it comes down to how the photocurrent varies with potential difference. That's really what it is. And so the first thing that we want to say is that, when we look at this, we see that we have a region here in region A, right, where what do we notice? There's zero, there's literally no photoelectric current, right? So let's write that in region A, what happens to the photocurrent is that photocurrent is zero, right? That's what we notice. That's what happened to the flow. There's no flow. So no flow of electrons. That's what that essentially means there. Why is there no flow of electrons? This is because the negative potential difference, we said that earlier, that there's a negative potential difference set up repels electrons from the anode. And so they never get there, hence current flows. And so that's why we say that in there, we're perpetually stuck at zero. Over that range, it's a range of negative potential difference. There is no current flowing because the electrons are just simply not reaching the anode. They're being repelled from the anode because the anode now had what? A negative potential, and the electrons don't want to go where it's negative, and so they just stay where they are, and they never quite get there. And so we never see a flow of electrons, and so we don't see a current in region A. Right? Let's look at region B now. When we look at region B, we see something interesting here, right? We see that there's like a gradual increase in that photoelectric current, right? And what's happening here is that our potential difference is becoming more positive now. You see that? So the electrons are starting to flow again and move towards the anode. All right, so let's write that now. So we see that the photo current increases, and it does so in a sharp way. So I would say sharply. Let's say gradual. That's more of a gradual thing. It doesn't like jump dramatically. So it's like gradually as the flow of electrons towards the anode starts to increase. And this is due to the potential difference between the anode and the cathode becoming increasingly positive. Okay, so whenever we have a positive potential difference, we will see flow. Okay, we'll see flow of the electrons to the anode, and as a result, we're gonna see a photocurrent associated with that. Okay, so that's what's happening in region B. All right, so let's talk about region C now. Let's take a nice look at region C. What do we see at region C, guys? We see that the photocurrent, right, it kind of maxes out. So it comes up and it kind of maxes out here, right? And it just stays at that level. It just stays at that level. So for this entire region of C, we see that we're like at a maximum saturation of the current, right? So it's called a saturation current when it like maxes out like that. So we call it a saturation current. We're never going to get higher than that current at this particular frequency at least, and this particular intensity at least, which we've already fixed. So this is a saturation current that we're seeing here. It's like maxing out. It maxed out, right? And so we have to explain that maxing out that we see, right? And so here's how we would say that then in region C. What's going on in region C? In region C, we can say that the photo current, which is maximum, known as the saturation current, right? This happens due to the fact that all, guys, all of the electrons from the cathode have now arrived at the anode. There are no more. There are no more to flow there. Right, so just think about it. The flow doesn't stop. But what we're saying is that all of the electrons that were at the anode now end up at the that were at the cathode now ended up at the anode. So there are no more to flow there. And this is what we see. We see this for a positive potential difference. Right? So this is a very positive region there. And so really and truly at the end of the day, there are no more electrons. They've all arrived there. All electrons emitted travel between the plates and they end up at the anode. And so the positive voltage values are gonna always show, you get to point saturation, it's gonna show like a constant current known as a saturation current. Okay, so that's what's happening there. So the rate of flow of charge is not changing because you've maxed out, and that's why your current doesn't change anymore. It just saturates. Okay, all right. And so with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on the left here, you'll see the next video up. And if you look on the right, you will see our Module 3 playlist, where you'll find tons more interesting content that will be helpful in getting you ready for this exam, okay? So thanks for watching, and we'll see you in the next video.